I'm going to present a paper on two-sided matching markets. And so with matching markets, I mean markets in which agents care about the identity or characteristics of the party they're transacting with. Okay? And so the standard examples for that are marriage markets, where you care about who you're getting married to, college or school admissions, where colleges care about student characteristics, students care about characteristics of the school, and preferences need not be well aligned. There may be a lot of heterogeneity in tastes across individual options. Also, if you find a doctor or a lawyer, a doctor may you may be interested in the experience of a person, of the professional. You may be interested in and the doctor may be interested in specifics of your case. And so this paper focuses on the one-to-one matchings with non-transferable utility. So non-transferable utility here means only that transfers, if they occur, are not negotiated at the level of the matched pair. So there are like many cases in which physical transfers actually take place, but they're determined outside of the matching. So for example, if I choose a doctor, the doctor will get paid whatever the going rate of my insurance is for a given procedure. In labor markets with centralized bargaining institutions, often a worker will get paid by the employer according to a schedule that takes into account the worker's experience, the design of the task, and so forth. And so this paper is about developing an empirical model that's tractable for this specific setting. And so the type of data I'm envisioning for this project, for this paper, is data on characteristics of matched pairs. So we observe a sample of matched pairs, and a matched pair may also just contain a single unmatched individual, and we observe certain characteristics of the two parties. And so we're interested in explaining the relative frequencies of matchings between types X of men and type Z of women. And so the problem for this is that if we assume any standard solution concept, for example, pairwise stability, then solving the exact model is very difficult. It's a very complex state space. I'm trying to give you an idea why, and I'm trying to give you an idea how we solve that in this paper. And so the objective of the paper is to find a tractable approximation to the finite market. So we're going to assume fairly standard setup for a random utility model where agents have specific preferences over individuals on the other side of the market. And we're going to assume a standard solution concept, pairwise stability with non-transferable utilities in the finite sample, and only that we take a limit of that model where we let the number of agents in the market go to infinity. Okay? And so the preferences have a relatively, so the main assumption on the payoffs is that they're additively separable. So we have what I'm going to call a systematic part that's a function of the observable characteristics of the woman and the man. And then there is an idiosyncratic taste shifter that I'm going to assume is independent of the systematic part. And the taste shifter is specific to both the agent who is choosing and the alternatives that she's choosing among. So there's a specific taste shifter for every man-woman pair in the market. And in addition to being able to being matched to a specific partner, every agent has the option to remain unmatched, to remain single. So that's going to be, in a discrete choice terminology, this is going to be the outside option in this problem. Okay, and non-transferable utility here means that the utility functions I wrote down here, these are the payoffs that the women and men in the market are going to receive once the match is determined, when the matching is realized. Okay? And so in this matching market, every individual can marry exactly one person of the opposite sex or choose to remain single. in order to translate the pairwise stability conditions into a discrete choice problem or a random utility maximization problem, essentially the crucial part is that we have to specify what the feasible set of alternatives to the agent is. And this is where essentially the central difficulty of the problem lies. So if I fix a matching in the market, then woman I can, in principle, choose any man that's available to her given that matching. And being available here means that that man prefers her, woman I, to their current spouse under the matching. Okay, so so J is in woman I's opportunity set, as I call it, if man J prefers her to his current matching partner. Okay, and so the pairwise stability conditions can then be translated into, so this is an equivalent statement of the usual textbook definition that a matching mu is pairwise stable if and only if everybody is matched to their most preferred alternative in their matching opportunity set. And so in order to see why this makes the task of solving the model difficult is that in the type of data that I just described, we do not know what alternatives are available to matching partners. Okay? So we have the opportunity sets are latent and they're endogenous. They're an equilibrium outcome of the problem. Okay? And so we're going to use the asymptotic approximation to simplify essentially the state space for this problem. But before we get to that, I just want to give a few commonly known facts about pairwise stable matchings that we're going to use over the course of the formal argument behind the approximation. So for one, if preferences are strict, and we're going to assume continuously distributed taste shift results, so with probability 1 that's going to be the case, then pairwise stable matching is known to always exist. And furthermore, the set of pairwise stable matchings has an ordinal structure where there's a maximal and a minimal element. So there's going to be a matching that's called the women prefer, the W preferred matching, which is among the set of all pairwise stable matchings, all women in the market agree that that they get a better matching partner under that matching than under any other pairwise stable outcome. And at the opposite end, there's also going to be a male preferred matching. So we can, for the argument, there are many important quantities that we can bound between those two extremal matchings. And that's very important for the formal argument. For inference, a problem is that we don't want to decide beforehand which pairwise stable matching is being played, which pairwise stable matching is selected. So this is very much akin to the problem of multiple equilibria in discrete games. And so the problem here is very severe if we think about increasing the size of the market. So there are theoretical results that essentially establish that the typical number of pairwise stable matchings increases exponentially in the number of market participants. So if they're more or less at the same, the size of the market on both sides, so the number of women and men is more or less of the same magnitude. The concept of pairwise stability as for an empirical model can be justified either if there is actually a centralized mechanism that solves for a pairwise stable matching. So there are a few institutional contexts in which that's actually the case. But also, there is essentially a tâtonnement argument that can justify pairwise stability. So as a result, by Roth and Van de Waart, that essentially shows that starting from any arbitrary matching, if we allow agents to myopically break up past matches and form new ones according to their preferences, then with probability going to 1, and if you let that process continue indefinitely, we're eventually going to converge to one pairwise stable matching. However, the specific matching that's being selected through such a process depends on the initial condition where the economy started, and it's going to depend on according to which mechanism we generate a sequence along which agents revise their matching decisions. So this means that we, in general, unless we don't want to make put additional structure in the problem, we have to worry about multiplicity in outcomes. So the model specification for payoffs is, as I said, going to specify a systematic part, and that's going to be the main empirical object of interest. And I'm going to show that knowing actually the sum of U and V is all we need to know to make any counterfactual predictions, to make welfare evaluations of the market outcome. And essentially that's going to be the empirically relevant quantity. So for the outside option, there is like a slight twist in how I set up the problem. So instead of having a single draw of the taste shifter for the outside option, I'm going to allow multiple draws. So in principle, there are j different independent ways of remaining single in this model. And the agent can just choose the maximum of those. And so the role of making the outside option attractive in the asymptotic experiment is going to be that we're going to see that the number of available matching opportunities for every given agent is going to increase in this asymptotic experiment. So if I draw an individual taste shifter for each of them, and the taste shifter distribution has unbounded support, eventually for any fixed outside option, I'll eventually come up with a draw that dominates the outside option. So in a naive asymptotic experiment where I just leave the outside option fixed, eventually all the agents are going to be matched to someone. And since I'm interested in the model as an approximation rather than a factual behavioral description of what would happen to real matching market if I increase the number of players, then I want to keep this aspect in the model. I want to keep that aspect in the limit of the model. And the second tuning parameter in the asymptotic sequence is going to be the scale of the idiosyncratic taste shifter. So for many standard specifications of this model, sigma can be thought of as held constant. In some cases, we have to be careful in that the maximum over a large number of independent draws has a scale that degenerates as we increase the number of draws. So in some cases, for example, for normal taste shifters, we'd have to increase the scale in order to balance the systematic and the idiosyncratic part of preferences. Okay, so the main assumptions on the systematic parts are relatively straightforward. So for the simplicity of the argument, I'm assuming that the systematic parts are all bounded uniformly in X and Z, and that they're p times differentiable. We don't necessarily need a parametric model for payoffs. And since I'm doing asymptotics for the data generating process rather than some estimator for a given model, this all doesn't assume a specific model for payoff. So I'm just holding taking the systematic parts as given. So the less straightforward part of the assumption is the distribution of the idiosyncratic taste shifter. So here I essentially assume the main assumption is that, for one, the taste shifters are independent of the systematic parts. But also I'm assuming that the tails of the distribution of the taste shifter essentially look like the tails of the extreme value type 1 distribution. Okay? And so this is not, if you think about parametric models that people might write down for this, this is not a restrictive assumption. So like Logit type specifications, normal taste shifters, as long as they're independent across alternatives, all fall into this class. And so the intuition for why I restrict the tails of the distribution is if I'm thinking about a discrete choice model where the number of alternatives becomes very, very large. And so the decision is made between essentially the highest ranked alternative that gives the largest random utility and the second largest. And so both of those are going to be, so the highest and second highest order statistic in a sample of random utilities, they're both going to be pretty far out in the tails of the distribution. So that the fact that the systematic parts are bounded essentially ensure that this is, that without loss of generality, I can focus on the tail properties of the distribution of the taste shifters rather than having to make restrictions on the central or the lower part of that distribution. Okay. And so the final piece that I need for the model, so the third and last set of assumptions, concerns the relative magnitudes of the different objects as I let n increase. So here, since the motivation for this analysis is to find a tractable approximation to the finite economy. So I get a data set. I know that the size of that matching market that the data came from is finite, is fixed at n. And I use an asymptotic experiment to essentially justify an approximation, to say that, to specify in which sense my approximation is close to the n-player economy. And so at first sight, this seems to introduce some level of arbitrariness. Like I can take my n-player economy, and there are infinitely many possible ways I can embed them into an asymptotic sequence. So I want to choose that asymptotic sequence in a way that it preserves the main qualitative features of the model. Okay, and so the two main features that I want to match in the limiting experiment is, for one, that I assume that in the real-world economy, I see unmatched individuals. I see singles, so I have to make sure that the share of singles doesn't degenerate at 0 or at 1 as I take that limit. So this is essentially going to determine how I change the outside option as I let n increase. The second qualitative feature that I want to match is I want the relative magnitudes of the idiosyncratic part and the systematic part of utilities to be balanced. Okay, I want them to be of the same order of magnitude. So if in the limit the idiosyncratic taste shifters dominated, then regardless of what the systematic parts were, essentially the limiting matching would be independent of the systematic characteristics x and z, and so there would be nothing to learn about the matching model. On the other hand, if the systematic parts dominate in the limit, then essentially, assuming away ties, I would essentially observe a degenerate assignment, non-stochastic assignment of types x to type z. And this is also not the kind of distribution that I have in mind that I want to model. And this essentially pins down the rates for both the scale parameter, and that's going to depend on the shape of the tails of the unobservables and the size of the outside option. Okay, so I'm not going to, so the problem with the matching is that in principle, I could keep track of all individual identities of agents in market, and it's under some matching, I is going to be matched to J, under some other matchings to J prime. But this is not the structure of the data set that I have. I assume that agents in that data set are unlabeled or essentially exchangeable. And that means that the only information that's actually in the sample is the distribution, the distribution of matched characteristics. Okay? And so I'm going to look at the joint. I take, say, look at couple-level combinations of xi and zj. If an agent is unmatched, then one of the components is missing. So that's also a possible value for each x and for x and z. And this is going to be the object that I'm going to approximate. And if I know that distribution, then I can, in principle, estimate parameters of a model using maximum likelihood. Okay? And so I'm assuming that if things are continuous, then this is going to be a continuous distribution. There's going to be a density. So I'm going to state the results in terms of the density of the PDF of matched characteristics. And so the main theorem of the paper essentially comes to that conclusion. So if under those three sets of assumptions, I can show that regardless of how the pairwise stable matching is being selected, the distribution of matched characteristics converges to a distribution with this PDF, which may be continuous, mixed, continuous, discrete, depending on what x and z is. And so to appreciate what's going on here, if for a minute we assume that u and v were both 0, so that the systematic part didn't matter for an assignment of matchings, then looking at the matching distribution in the top line, essentially the matching frequencies would just be a product of the marginal densities of the characteristics x and z. Okay? Up to a scaling factor, so 1 over gammas, the 1 over gammas essentially, 1 over 1 plus gammas essentially specify the share of singles of a given type. And this depends on quantity that I'm going to call the inclusive value function. And this auxiliary parameter that's not specified in the model is determined by equilibrium conditions on this function. Okay, so if I want to estimate a model of this kind, I can estimate it using constraint maximum likelihood. I can use the matching frequency distribution to write down a likelihood function, treating the gammas as nuisance parameters. And then I can impose the equilibrium conditions on the inclusive values functions as additional constraints in the maximization problem. So to see, I just want to give some idea where that asymptotic result comes from. Okay, so the main insight or the main stepping stone in this asymptotic experiment is to realize that essentially the relevant discrete choice model for this in the limit becomes conditional Logit. Okay, so I'm going to show that this is essentially the first step of the argument is that the conditional choice probabilities for a given realized opportunity set look like multinomial, like the conditional choice probabilities of multinomial Logit. And so this dramatically simplifies our problem. So the central problem was that the opportunity sets were unknown. They were random and they were determined in equilibrium. So if I want to see how the opportunity sets enter conditional choice probabilities, I just have to look at the denominator here. And the denominator is what in that literature is called the inclusive value. So the sum over exponentiated systematic parts of utilities are a sufficient statistic for the choice set M with respect to the conditional choice probability. Okay, so if I don't know M, if I don't know the choice set, but I know the inclusive value, then I know all I need to know to compute the conditional choice probability. So instead of having to keep track of this combinatorial latent state of which exact men or women are available to each other, I just have to keep track of the inclusive values. Furthermore, the inclusive values, they're a sum of individual contributions. So if I know that these are drawn from some distribution, this works like a sample average. And I'm actually going to find that this is also the right way to normalize this in the limiting experiment. So the inclusive value is also going to be a sample average to which I can apply a law of large numbers. And so what's going to happen essentially is that all women of the same observable type are going to face the same distribution of opportunity sets, and they're going to evaluate the matching prospects in the same way according to the same the same systematic utility component. And so there's going to be a conditional law of large numbers that's going to show that as the market grows thick, all women of a same or similar type are going to have a similar inclusive value. And therefore, similar conditional choice probabilities among a set of matching prospects. Okay, and so the main structure, the main line of reasoning of the proof goes as follows. So the first thing we have to take care of is that opportunity sets are endogenous to each agent's own taste shifters. So especially if I look at a very simple small model with like 2 or 3 players on every side, if my own taste shifters over alternatives change, that changes who I'm available to. If I'm no longer available to somebody who would have chosen me, then that person starts picking somebody else. And so there's potentially a chain that might percolate through the entire market and affect my own opportunity set. So in the finite sample, my own opportunity set is a function of my own taste shifters. And so this is a part of the central endogeneity problem. And what we find is that this dependence vanishes fast enough for our purposes as the market grows large. So the probability of a feedback from my own preferences into my own choice set goes to 0 as n goes large. And then one can show that everything, all the interesting action with random utilities happens in the upper tail of the random utility distribution. So I'm in the conditional Logit world. And then I only have to care about inclusive values. Once I only have to care about inclusive values, I can find a law of large numbers. I can prove a law of large numbers on those inclusive values and show that they converge to objects that are only functions of the type. And those functions satisfy a fixed point, are determined by a fixed point condition. And that fixed point mapping turns out to be a contraction. So there's always going to be a solution, and it's going to be unique. And then one can show that the fixed point mapping converges in a way that ensures that the solutions to the fixed point mapping also converge. So this is the rough outline. And so depending on time, yeah, I think I'll have a little bit of time to just explain at least roughly or give a sketch of the main. Yeah.
Question. Does this result really, suppose that I have unobserved types and they kind of sort in the market. So they know what's going on, but I'm the econometrician observer. Is that covered in your case? I mean, in other words, if I have these like markets going on where I have people, say a finite number of types, male and female, like personality types or something of the sort, so that's going to be giving me dependence within the market. And they're going to sort of within the market, but you're not going to know that looking at your aggregate data.
Yeah.
That's going to create a kind of dependence, which I think may be ruled out.
Yeah. So I think so. If I understand this point right, I think the point where it's ruled out is essentially in the size of the systematic parts. So the systematic parts may include unobserved types, and then that they are on that part is on the same magnitude as those completely independent IID draws of taste shifters that make sure that all possible subsets communicate with each other. So essentially,
I was thinking more like stratification.
Yeah, yeah. So this kind of keeps this rules out the stratification of that. So this is where this independent unbounded support taste shifter that has it remains on the same scale as the systematic parts, where that essentially. So we can, if there are for systematic types, systematic parts of payoffs in between combinations that are arbitrarily large or plus or minus infinity, then that would essentially be the boundary from describing one market and several segmented market. And I would have to know along which lines those are segmented. Yeah. And so location can be part of X and Z. So the dependence argument essentially looks at what happens if I replace the taste shifter. So I look at a given market outcome, and woman I has a specific realization of those taste shifters, eta I. So what happens if I replace that with an independent copy from the marginal distribution of taste shifters? So independent of that pairwise stable matching and of all the types in the market. And so essentially, I have to show that the probability that that shift ultimately affects woman I's opportunity set becomes small as the market grows. And essentially, what's going to happen is that if so before, under the alt realization, woman I had a preferred matching partner in her opportunity set. And now with the new taste shift, there's going to be another most preferred matching partner. But any changes can just come from those two. If a man was unavailable to woman I before the taste shifters were changed, then if woman I doesn't prefer them to their current match anymore, it doesn't matter. Like it doesn't affect their decisions. It doesn't affect because they already have a better alternative to go with. So essentially, and at every subsequent step in such an imagined chain, at every step there's only going to be the previous match that might be affected by such a chain. Okay, and so at every step in this chain, there is a chance that this next best option is actually the outside option. And so the outside option can absorb such a chain of adjustment. On the other hand, it can, at every iteration, I herself can be the next one in the chain. And so those are the feedbacks that we're trying to rule out. Okay, so graphically, if I rejects a man that she had previously chosen under the old taste shifters, then that man might either might either choose to remain single once I is no longer available, or might choose become available to another woman that was in his opportunity set. And so at every stage, there's a probability that's non-trivial that this next best option is the outside option, in which case such a chain terminates. And then there's a probability that's essentially symmetric among all market participants. So it's essentially of the order 1 over n that the next chosen individual is going to be that specific woman I. Okay, so whenever the chain goes back to woman I, that closes a preference cycles. And the preference cycles of this type that also essentially support multiple pairwise stable matching. So if there were no preference cycles of this type, of this kind, there would in general also be theoretical results that show that then there would also be no multiplicity of pairwise stable outcomes. The next part of the argument is essentially considering the shape of the upper tail of the taste shifter distribution. So this is, I didn't put that, the argument on the slides this time. And then to see why inclusive values become more similar across individuals of a similar type. So those inclusive values are essentially sample average. And we can we show that the size of the opportunity sets increases at a root n rate for every individual in the market, so that this is in fact a proper sample average over the endogenously available individuals. And the probability that, say, man J becomes available, ends up in this opportunity set, depends on that man's utility and his inclusive value. Okay, so this is turns out to be also the mean, the conditional mean of those inclusive values, and the difference between the two is a weighted average of indicator functions, availability indicators minus their conditional probability, and then one can show that there's dependence across those indicators is sufficiently small for a law of large numbers to apply. And that law of large numbers is also uniform with respect to x, because those weights in the first before outside the bracket, like they satisfy a VC condition. Okay, and then one can, if we know that the inclusive values are close to the inclusive value functions by a continuous mapping argument, I can replace them in this condition. And essentially, I get a fixed point representation of the inclusive values. And the fixed point mapping is also a sample average that's going to converge by a uniform law of large numbers. Okay, and one important part now in the argument is that the fixed point mapping happens to be a contraction. And the contraction constant depends on the upper bounds on the systematic parts of utility. So if and this 1 plus comes from the outside option. Okay? So we saw that in the dependence proof, the outside option was crucial in absorbing those many of those feedbacks. And here it's crucial for ensuring that the inclusive value functions are uniquely defined, and that that there is a unique solution to this problem. So then, putting those arguments together, I essentially get to this. I get to this matching distribution. And so maybe I should briefly say what qualitatively goes on here. So in terms interpreting the model or the asymptotic experiment economically, there are essentially like 4 qualitative features of that experiment. So for one, all agents have a large number of matching opportunities that's available to them. And similar agents have similar options in terms of the composition of their opportunities, but most importantly in terms of their inclusive value. So this is the law of large numbers step. And even though the number of different pairwise stable matchings, so one can see that in simulation experiments, actually increases as n grows, the degree and amount of multiplicity doesn't increases slowly enough to ensure that the resulting distribution, at least, is unique. So there is, from the agent's perspective, there may be a lot of multiplicity here in the economy. It's just that it's just not revealed to the outside observer. So all those pairwise stable matchings result in the same distribution. And so to see now what we can do with this limiting approximation for identification, for estimation, so the first realization is that if you look at this expression here, U and V always show up as the sum, both in the distribution, both in the PDF and in the constraints. So that means that I can just replace UXZ plus VZX with WXZ, and I can just reparameterize the entire problem just in terms of the sum of the two. So that means that U and V are not separately identified. Okay, so from the matching outcome, I can't tell whether Anne is married to Bob and Angelina to Brad because Bob doesn't like Angelina, or just because Angelina likes Brad more than him. And so in a finite economy, there may be a chance that we may be able to figure this out. But in the limit, any such identification result must break down. On the positive side, we can actually solve for that surplus function in closed form based on the matching distributions. And so this is a non-parametric identification argument. One thing that's a little bit, maybe a little bit irritating about the surplus function is that in the original model, there's no numeraire. There are no transfers. And still, we add up two utilities into a surplus, even though there is no way of splitting that surplus. So U and V essentially are parameterizations, are descriptions of a random utility model. They characterize the statistical properties of preference orders. And so, for example, if min just didn't care about any systematic characteristics at all, because they had very large the taste shifter distribution had a very large variance, then that would just inversely normalize their component, so they wouldn't add much to that surplus. Okay, so we can also give the inclusive value of welfare interpretation. But I think it's maybe better if I just briefly show some simulation results. So I solve the matching market using the Gale-Shapley algorithm, which gives me the two extremal matchings. And so if I want to understand how much multiplicity there's going on in the model, I can actually bound many objects of interest between those two extremes. So for example, here I'm comparing the number of men that are available to woman I under the female versus male preferred matching. Any other matching, pairwise stable matching, has to be somewhere in between. So this gives me an upper bound of how far they are apart. And I see that that average number actually decreases to 0. But if I use a different measure, if I look at for how many women does their opportunity set change between the male and the female preferred matching, that number actually increases. But it increases slowly enough for it not to affect the resulting matching distribution. And so for estimation, I just choose a simple parameterization of the model, and I normalize the parameters in a way that I only estimate surplus parameters. And I estimate this using a constraint maximum likelihood, which is really straightforward, even with a standard optimization routine in MATLAB. So I find here that as n increases, the size of the market grows, the bias of the maximum likelihood estimators vanishes, but it vanishes more slowly than biases of nonlinear estimators typically vanish if the approximation was in the estimator, not the DGP. So here's an important difference in the types of asymptotics that's happening in this paper and the way we usually think about asymptotic properties of estimators. So these are estimators that are obtained from a single realization of the market. And the approximation here is an approximation for the data generating process. And so the maximum likelihood estimators are functions of this wrong but close approximation. And this is not just an issue of a bias from nonlinearity, which is typically of order 1 over n. So actually we find that the simulation results suggest that the bias is of the same order as the standard deviation for these approximations. The limiting model, so this is essentially a part of like a broader agenda where I'm look at game theoretic models or models of strategic interaction where asymptotics can be used to simplify the structure of the problem. So usually the main theme is going to be to identify aggregate state variables that at least in the asymptotic approximation are sufficient statistics for equilibrium quantities and are a sufficient parameterization of the limiting experiment. So in this example here, that state variable those state variables are the inclusive value functions. So in the inclusive value functions are not sufficient to characterize the exact finite sample distribution of the problem, but they become sufficient for the limiting problem. And here in this case, the problem is relatively, the limiting problem is relatively benign because there's no multiplicity in the limit. But finding aggregate state variables of this kind can also help deal with issues of multiplicity. So multiple equilibria may generate different distributions, but being able to consistently estimate those aggregate state variables may give us a sufficient statistic. So with conditional inference, we may actually completely resolve the multiplicity issue. Right.
Okay, thank you very much for leaving something to the discussion. So I would like to say first, as a first liminal comment, that I'm going to repeat what Phil said about Paulo's paper. And this is really a tour de force, and this way I get to speak French. So there are a number of major achievements in this paper, and my discussion is going to pass completely over them because instead of working with the very hard, very difficult approximation problems, and one of the main contributions of the paper is to show actually how you can go to the limit in a clean way and rely on these aggregate quantities. I'm just going to go almost directly to the limit and try to understand what are the assumptions that are driving the result. But again, this is remarkable. There's been a lot of work on transferable utility in various frameworks, Jeremy's, Chu and Sayos, and Savagnier, Chiapori, Galichon, and others. But the TU problem is really fairly simple. It's linear programming. And it works very nicely. You don't have to do limit arguments because even with a finite number of agents, you have a unique matching. And yes, you have to, if you want to do things more neatly, you do limits, but they're really very simple limits. This is much more difficult because problems with non-transferable utility are not linear programs. They're combinatorial problems, and they're much harder to work with. So I'm not going to rephrase Konrad's argument. One thing I should say also as a liminal comment is that it's a bit of a sad occasion in a way. It's that I've been to a lot of matching preferences, included by myself when Gary Becker was in the audience, and so I'm missing him today. I'm going to use the indices that Konrad used, J for man and I for woman, although the first thing Gary would have said in your seminar is, this is marriage, there is transferable utility, man. So when I say man and woman, let's just, they are virtual man and virtual woman. Real men and women transfer utility, it's a well-known fact. So despite that, there is a first mystery in this paper, which is that we get to add utilities. So how does that come up? We are adding U and V, but so it's partly normalization, but there must be something deeper going on. So that's the first result. Not only do we get to add utilities, but that's the only thing we are going to identify from the model. The second thing is that we get this really neat formula. Again, Gary Becker would have said matching is about complementarities in joint surplus, he would have said, not pseudo surplus. And here I'm using a notation that should be obvious. DHZ just take the difference in the H direction and then the difference in the Z direction. So it's a cross difference operator. Why do we care about this operator? Well, because Gary showed in 1973 that if you have positive complementarities between two characteristics on the two sides in the formation of joint surplus, you're going to get positive assortative matching along these characteristics. So here it's really nice. You want to know whether there is complementarities in the joint surplus, W, or the pseudo surplus. You just look at the log of the number of matches that involves somebody with type H and somebody with type Z. But again, so how does that come up? That's a bit of a mystery. So we are going to try to solve these mysteries. By the way, Chu and Sayo, which is the framework, one of the frameworks in transferable utility, one I've worked on a lot, they have a 1/2. So you don't have a 1/2. That's another mystery. You might say, well, I don't really care because I care about the sign of complementarities. The 1/2 is not going to change that. So the questions are, what assumptions really matter? Does it matter that it's non-transferable utility as opposed to transferable utility? Does it matter that within every type H there is a lot of I's, within every type Z there is a lot of J's? Does it matter that there are many H's and Z's? Does it matter that, so I'm writing Gumbel because type 1 extreme value is a little bit boring, but you can think of it as Logit. So does it matter that we are choosing this idiosyncratic and IID shards in the maximum domain of attraction of the Gumbel distribution so that the maths converges to Gumbel? Does it matter that they have the same variance? So this one is silly, so I'll pass on it. Does it matter that they are IID? So I'm going to try to give answers to that, so it's going to take us about half an hour. The first answer is non-transferable utility versus transferable utility. It actually doesn't matter that much. And there is a paper by Alfred Galichon, and I should say that discussions with Alfred have inspired a lot of what I'm going to say. Scott Cominus and Weber that actually does imperfectly transferable utility. So both cases and everything in the middle for a specification that is close to Logit. But it doesn't dominate Konrad's paper. That's not what I meant. So having many I's within H, many J's within Z, that's going to be vital. Many H and Z, that's practically irrelevant. I would encourage Konrad to look at the different types of extreme value distributions. For instance, straight people, when they do matching, they use Fréchet. So it would be interesting to know what happens. Also, you get typically faster convergence to Fréchet than you get to the Gumbel. The same sigma is not interesting. Now, the eta and zeta that are the idiosyncratic shock are IID, so we are going to work a little bit on that to get us closer to the Galichon-Salagnier family of papers. But first, I want to give a sort of intuitive and sloppy explanation of what Konrad is doing. And again, I'm going to completely waive the approximation difficulties. So I'm not sure it will be more intuitive than what Konrad did, but at least I can guarantee it's going to be much sloppier. So the first thing I'm going to do is I'm going to drop singles. So nobody is allowed to be single. I started life as a contract theorist, so we do simple mechanism design. If you stay single, you will be shot. So everybody has to be matched. It just makes it simpler, and I don't think it actually detracts from what Konrad is doing. So the fundamental equation is this. This is the fundamental coupling equations to speak like an applied mathematician. The utility of a woman I in equilibrium at a given stable matching, you have to fit one because there might be several, is the maximum of these utilities conditional on the fact that anyone she wants to marry has to accept her. And who will accept her? Well, a man to whom she would give a utility that is at least as high as what the man is getting in equilibrium. So that's what Konrad calls the opportunity set. Now, Konrad wants the zetas and the etas to be in the domain of attraction of Gumbel. So I'm going to assume I have logits to start with. It's just so you don't have to worry about that part of the limit argument. In that case, we know the logits or the Gumbels are match stable. So the match of logits is a logit. So this UI, I can break it down as a U that depends on the observed type of the woman, which I call U at psi, plus an eta bar I, which is also a logic term with the same variance as the ones we started from. Now, this U8 is just going to be the standard log H formula, log sum formula, sorry. Except the sum is on a messy thing because you have to sum over the men who will potentially take that woman. Now, so we have to count the number of men in every type Z who are going to be available to that woman. So how do we do this? Well, the men who are going to be available, they're the one to whom this person would guarantee a utility larger than their VJ. But remember, I said that the UI is a logit. Well, the VJ is also a logit because I could have done the same argument on the other side. So now I have one logit on the left-hand side and one logit on the right-hand side. So I know what this is. It's just this super simple formula. The number of men, this is the number of men of type Z that are going to be available to this woman I, just this formula here. Now, in addition, there's a lot of i's, and in the limits that they're going to be like square root of n. So this VZ, which is the max, is going to be much larger than the capital V. So this 1 over 1 plus the exponential, it's almost the exponential of minus. So I get this really nice formula, sorry. And you can start to see where the U plus V is going to come about because there's the choice on the side of the man, which is going to generate an exponential of U because we have a logit. And then there is the acceptability on the woman's side, which is going to generate an exponential of V because we have a logit. So we get exponential of U plus V. That's how I'm going to get my W. So if I go back to my U8s, I put things together, and I get this, which is a Kaplan equation. It looks very much like a Kaplan equation you would get with TU, actually, transferable utility. So to answer your question, there's Jim's question. There's a lot of convergence there. So there is one equation that gives you the U as a function of V, and one equation that gives you the V as a function of U. And if you write this as exponentials, they're fairly simple equations, and Konrad proved their contraction using, exponential of the things I've written as arguments. So you can even write them in a more symmetric way, just to say, take the exponential of the joint surplus, sort of, minus the utility of the man minus the utility of the woman. Take the average over all possible types of men. That has to be 1 for every type of woman. And the same for every type of, well, the other way around. Matching is painful because you have to write everything twice. So how did the W come up? I've already explained. Probability of proposing to someone is exponential of U. Probability of being acceptable is exponential of V. And then you just have to, multiply these two things. So I'm going to drop this. This is not interesting. So the second important part of what Konrad does is to say, well, it's really simple to estimate because all I have to do, well, again, it's a caricature. But the core of what I have to do is to look at the choices of women of type H choosing men of type Z. And then this is this formula. You have to be careful about the number of men who are available again. But you do this sum, and you're going to get, remember, NZ of H is exponential of V, more or less. So you're going to get the exponential of W, and then there is this messy denominator, but the only thing I care about is it's a function of H, not of Z. So when I'm going to take this cross operator, this cross, blah, 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 yes, this cross derivative operator, this is going to vanish, and we just get this. DHZ of log of F is DHZ of W. So this is very easy to infer the complementarity in a pseudo surplus. Now, go back maybe to Jim's question. I'm not sure I understood it, but then there's a lot I don't understand that comes from Jim. So then, so suppose we put some interactive effects, just like Chu and Sayo, in addition to the etas and the zetas. The etas and the zetas are still completely IID across I and J, but I'm going to add some effect of, you could call it preferences of man I towards women of type Z, except I interchange women and men, and you do the same for the other one. So you do like Galichon-Salagnier, and you're going to say, well, these vector things, because this is a vector indexed by Z in the first equation, for instance, so there's as many dimensions as there are values of Z. That's why there are bold letters there. It could have a distribution that depends on 8, and the same for the other one. What can I say? I'm still going to assume that the zeta and the psi are going to Gumbel. And then, I mean, if I did the math right, I'm not absolutely certain, then you get, remember I had an equation that says W minus UH minus VZ, and the average had to be equal to 1. So here you get something a tiny bit more complicated, because you're going to get this plus F here, but they are not random. I mean, they're random, but they're not in expectation, sorry. And you're going to get these conditional expectations. So it's still possible to do this. You can still work with that. And if that's correct, that's a pretty interesting extension, because you don't have to stick to this really IID framework. So what changes? Well, obviously, only W is identified still. That doesn't change. You don't see U and V separately there. So you're going to get W. You have a fixed point in function spaces, which is a bit more trouble, but it should work. I'm always very optimistic about these things. And then when you take the cross derivative operator, you're going to get these two additional terms. Now, it doesn't really matter what they are. They're like the Legendre-Fenchel transforms in my paper with Galichon. They play pretty much the same role, but there is one special case that's interesting. So these things are nasty because there's both H and Z. There's Z in the conditional, there's a VZ, there's a UH, there's an FZ and an FH. So they do have a cross derivative that does not vanish, but there is a case in which they do vanish. First, assume that there's many values of Z. Then FZW is independent of the vector FW, sort of, or at least the value. It's independent of the value UH of FW. This is the kind of argument that Konrad will make much more cleanly. I told you it would be sloppy. And then there is the second thing. Now, the second thing is not a problem. It only depends on H now. So it's going to go away when I do DHZ. The first one still has H and Z. So how do I eliminate this? Well, I'm going to say the distribution of this FW does not depend on H. So this is saying women of a certain type have a distribution of preferences over the types of men that do not depend on the type of that woman. Okay? So I could have correlation between my preferences for various types, but my correlation structure does not depend on my type. And then in that case, you're done because the DHZ or the other term is 0, and you get this remarkable result, which is still, you just have to look at log of F, which is directly observable, in order to infer the complementarities in the joint surplus. Not the joint surplus itself, which is more messy, but the complementarities on the joint surplus. All right, I'll just stop there.
Thank you, Bernard.